Welcome to Heraverse. Today, we step into a quiet corner of the cosmos, where an interstellar comet called 3I Atlas crosses our solar system, and where even the CIA refuses to confirm or deny what it knows. If you enjoy mysterious science stories like this, please like the video, subscribe to Heraverse, and share it with someone who loves cosmic mysteries. Thank you for watching, and for helping this universe of stories grow. In the years leading up to the appearance of the object that astronomers now call 3I Atlas, the idea of interstellar visitors to the solar system slowly moves from speculation to data. Sensitive surveys watch the dark sky for faint streaks, and a small number of objects are found on paths that never close back into the familiar shapes of bound orbits. These first cases are rare and already surprising, but they still resemble ordinary comets in many of their properties. 3I. Atlas enters this scene as another point of light. At first, just one more moving dot in a catalog of many, until its motion reveals that it does not belong to the Sun in the usual way. The object approaches from the outskirts with a speed and trajectory that show it is not tied to the solar system. Its orbit is open, a hyperbolic path that carries it in, around, and then out again, toward the deep background between the stars. This alone already marks it as a visitor from far away. A piece of material that formed under different conditions and has wandered for an unknown length of time through interstellar space before crossing the planetary plane. It is not the first such object, but as measurements accumulate, it begins to look like one of the strangest. When astronomers trace its path backward and forward, a quiet pattern begins to emerge. The object does not simply slice through the solar system at a random angle. Its motion lies close to the plane in which the planets orbit, within only a few degrees of the ecliptic. For a natural visitor drawn from a distant cloud in a random direction, this near alignment is already statistically unusual. The fact is noted, commented on, and then set aside as a possible coincidence. The solar system is large, survey biases exist, and chance alignments are not impossible. Still, in the background, the first entry in a growing list of geometric curiosities is made. As 3I Atlas moves inward, observers watch for the same behavior they expect from ordinary comets. Near the Sun, ice should sublimate, and gas should stream away from the nucleus, dragging fine dust into a diffuse tail that points roughly away from the Sun, under the combined push of radiation and the solar wind. At first, the object seems to comply. Activity is seen, material is being shed. But careful imaging reveals a structure that does not match expectation. Instead of a simple tail that streams away from the Sun, a prominent jet appears to point almost directly toward it, forming what observers call an anti-tail, a narrow feature extended in the opposite direction from what most people think of as the tail of a comet. This is not entirely unprecedented in comet science, since projection effects in geometry can sometimes create the appearance of a tail that points sunward. Yet, the jet of 3I Atlas is unusually long, unusually straight, and unusually persistent. Estimates suggest that the structure extends over hundreds of thousands of kilometers, a length comparable to the distance between the Earth and its moon, while remaining about an order of magnitude narrower than its length. That kind of aspect ratio, combined with the direction and stability of the feature, is difficult to reconcile with simple models of gas and dust blown freely by sunlight. The jet becomes one of the central puzzles attached to this object. By the time dedicated studies start to appear, astronomers have already given 3I Atlas a place in their ongoing effort to understand small bodies that wander between the stars. Observations from ground-based telescopes and from space-based instruments like the Hubble Space Telescope show that the nucleus is active, that jets of material are emerging from its surface, and that the structure of those jets is complex. A prominent jet points toward the Sun, and a fainter one points roughly away, together forming a kind of two-sided system that seems to wobble over time. The wobble hints at rotation, suggesting that the surface of the object hosts localized active regions that sweep around as it spins. Light curves, which track how the brightness of the object rises and falls, repeat with a period that matches the apparent motion of the jets. From this, astronomers infer a rotation period of roughly several hours. The object spins, sheds material, and interacts with sunlight and the solar wind in a way that is broadly familiar, but the details resist simple classification. As the months pass, another key date takes shape on astronomers' calendars. In late January of a given year, the Earth, the Sun, and 3I Atlas will fall almost exactly on a straight line, with the Earth placed between the Sun and the object. The angle between the incoming sunlight and the line of sight from Earth to the object, known as the phase angle, will shrink to a very small value, less than a single degree. This geometry is known as opposition. It is the configuration in which a full moon appears, and it is also the configuration in which light scattered by dust can show a sharp surge in brightness. This increase, called an opposition surge, arises from two effects. One is purely geometric. When dust particles are viewed at very small phase angle, their illuminated faces are turned fully toward the observer, maximizing the visible cross-section, much like the full face of the moon. The other is more subtle. At these small angles, scattered light can add coherently, a process rooted in wave interference that makes the back-scattered light brighter than simple models would predict. 3i Atlas will pass through this configuration on a specific night, and the coincidence of its interstellar status, its strange jet, and this rare, near-perfect alignment captures attention. The event turns the object into a natural laboratory for studying its dust and gas. Observers realize that by measuring how much the brightness jumps at opposition and how the polarization of the light changes, they can infer the size, composition, and structure of the particles being shed. The particle sizes already appear to be large compared to those from typical comets, perhaps tens of micrometers across, rather than the much smaller grains often assumed. Larger grains feel weaker pressure from sunlight for their mass, so they are harder to push into a broad, sweeping tail. This fits with the absence of a prominent tail pointing away from the sun, and with the presence of a narrow anti-tail that appears to resist radiation pressure. All of this can be framed in terms of known physics, but the combination of traits continues to stand out. An interstellar origin, a path close to the planetary plane, a jet aimed toward the sun, large and persistent dust structures, and an upcoming opposition geometry with an unusually small phase angle form a cluster of facts that is not easily dismissed as routine. At this early stage, official interest is still mostly confined to the scientific community. Observatories schedule time, papers are drafted, proposals are submitted. Yet outside the public record of journal articles and telescope logs, other institutions also begin to take notice. In a world accustomed to sudden, low-probability, high-impact events, the idea that an unusual interstellar object might merit quiet assessment by agencies responsible for security is no longer far-fetched. Somewhere, requests for information are filed, and questions are asked about what is known and what remains uncertain about this visitor. Long before any formal answer comes back, 3i Atlas is already on its way inward, carrying its unresolved anomalies with it. As the date of the opposition approaches, the behavior of 3i Atlas becomes the focus of a quiet, concentrated effort across observatories on Earth and in orbit. The geometry that is about to unfold is simple to describe, but rare in practice. On a night near the middle of January, the Earth passes almost exactly between the Sun and the interstellar comet, so that the Sun, the Earth, and the object nearly share a straight line. The angle between the incoming sunlight and the line of sight from the Earth to the visitor shrinks to a very small value, less than a single degree. In comet science, this configuration is known as opposition, and in that configuration, dust illuminated by the sun can show a sharp and diagnostic brightening. For 3i Atlas, this moment is not only visually striking, but also scientifically valuable, because it offers a way to probe the dust and gas surrounding the nucleus under a very specific set of conditions. Astronomers expect that as the phase angle drops towards zero, the brightness of the object as seen from Earth will rise beyond what a simple reflection model would predict. Part of this is straightforward geometry. When small particles are illuminated and then viewed almost directly back along the path of the incoming light, their fully lit faces are presented to the observer, much as the face of the moon appears at its fullest when it stands opposite the sun in the night sky. The deeper part of the effect comes from the wave nature of light. At very small phase angles, scattered waves from different parts of a grain can add coherently, reinforcing one another and producing an enhancement in the intensity of the backscattered light. This combination of geometric full illumination and coherent backscattering is known as an opposition surge. It has been studied in planetary rings, in regolith on airless bodies, and in the dust comas of comets. For 3i Atlas, the expected surge is not just a detail. It is an opportunity to measure the size and texture of the dust grains in the strange anti-tail, using the sky itself as a controlled experiment. The observing plans reflect this sense of opportunity. Professional facilities with mirrors larger than about 1 meter schedule time around the opposition date to track the brightness and polarization of the object over many hours. Smaller telescopes operated by dedicated amateurs prepare to monitor the antitail and the overall morphology of the coma, adding coverage at times and locations that large observatories cannot easily reach. Space-based instruments, free from atmospheric turbulence and weather, provide stable imaging across multiple dates before and after the key alignment. The aim is simple in principle. Measure how bright the object becomes at exact opposition compared with nearby days, and measure how the orientation and strength of the polarization change as the angle between the object and the sun sweeps through its smallest values. On the night itself, the geometry quietly locks into place. The sun drops below the horizon for observers on the night side of Earth, and 3i Atlas rises in the opposite direction, lit from behind their vantage point by the same star they no longer see. Telescopes gather photons that have left the sun, struck dust grains in the coma and the antitail, and returned almost directly back along the incoming path. When the data are calibrated and compared, the brightness profile reveals the surge that theory predicts, but its character is not entirely routine. The increase in brightness near exact opposition is clear and measurable, stronger than would be expected from a coma dominated by very fine dust. The pattern suggests grains that are large on the microscopic scale, tens of micrometers across, rather than the much smaller grains commonly invoked for other comets. Large grains have less surface area relative to their mass, so the pressure of sunlight is less effective at accelerating them away from the sun. This conclusion fits the absence of a broad, diffuse tail directed away from the star, and the presence, instead, of a narrow, elongated structure pointing sunward. The opposition surge therefore supports the idea that the anti-tail of 3i Atlas is not a fragile spray of fine smoke-like particles, but a collection of more robust grains, heavy enough to resist being swept back into a conventional tail. At the same time, polarimetric measurements add another layer of complexity. Polarization describes the orientation of the electric field of the light wave as it travels. Reflected sunlight can become polarized in specific ways depending on the size, shape, and arrangement of the particles that scatter it. Many comets show a broadly similar pattern of polarization as a function of phase angle, with modest values that become more positive at certain angles. Previous observations of 3i Atlas, taken at phase angles somewhat away from exact opposition, have already shown that its polarization behaves in an unusual way. The light from the object displays negative polarization in a range and magnitude that appear extreme compared with the comet population recorded so far. Negative polarization means that the electric field oscillations tend to align in a direction that is opposite to what is commonly expected from scattered sunlight under similar angles. This property alone makes the object stand out, and researchers publish early reports describing the signature as unprecedented among known comets. Around opposition, new polarimetric data refine this picture. As the phase angle decreases toward its minimum, the polarization signal evolves, but instead of sliding smoothly into line with existing models, it preserves its strange character. The combination of a strong opposition surge and extreme negative polarization suggests a complex internal structure of the dust grains, or a particular arrangement of particles in the coma and the antitail that current scattering theories struggle to match. Ideas are put forward involving fluffy aggregates, layered grains, or mixtures of ice and refractory material with specific porosities, but none of them provide an entirely comfortable fit to all of the data at once. The light that returns from 3i Atlas at opposition therefore carries a kind of double message. On one level, it confirms well-established physical principles, such as the enhancement of backscattered light at small phase angles, and the sensitivity of polarization to grain properties. On another level, it adds to the list of anomalies associated with this interstellar visitor, because the exact way in which the light brightens and polarizes refuses to settle into the familiar patterns learned from decades of studying ordinary comets bound to the sun. When astronomers place the new results alongside earlier findings, the sense of an accumulating pattern becomes more pronounced. The orbit is interstellar and yet lies close to the planetary plane. The jet that points toward the sun extends across a distance comparable to the separation between the Earth and the Moon, while staying remarkably straight, implying large and resilient grains. The negative polarization is stronger and more persistent than in other cases. The timing of the near-perfect opposition alignment falls within a narrow window during which the object is active and observable, even though its total journey from the distant cloud to the inner solar system spans many thousands of years. On its own, each of these features can be filed under the category of unusual but perhaps natural. Together, they begin to look like a cluster of low-probability traits that invite closer scrutiny. In discussions in conference presentations, the emphasis remains properly cautious. The data justify talk of a rare configuration, not of intent or design. Yet, in parallel, a more speculative question hovers in the background. If an object were constructed or guided by a technological civilization for some purpose that involves collecting or transmitting information, might it choose paths and orientations that exploit gravitational fields in optimal illumination geometries in ways that happen to resemble what is seen here? This line of thought is not presented as a conclusion, only as a possibility worth keeping in mind as the anomalies stack up. It is anchored not in fantasy, but in the measured peculiarities of the light and the geometry. For now, the focus stays on extracting as much information as possible from the opposition data. From the brightness enhancement and the shape of the surge curve, researchers constrain the typical grain sizes and their scattering properties. From the polarization pattern, they infer that the grains may be composed of materials and structures not commonly dominant in the come of bound comets. These inferences, in turn, inform models of how the nucleus of 3I Atlas might be built, how it fractures, and how its internal layering responds to sunlight. The night of opposition has passed, and the object continues along its path. But the measurements taken in those hours add a dense new layer of facts to its dossier. Somewhere in that layer, beyond the immediate interpretations, lie clues that will later intersect with findings from imaging campaigns and dynamical calculations, and will eventually attract the attention of institutions that usually reserve their concern for events closer to Earth. For the moment, however, the story remains framed as a challenging problem in cometary physics, illuminated by a rare, nearly perfect alignment that throws the strangeness of this interstellar visitor into sharper relief. In the weeks surrounding the opposition, the shape of the material around 3I Atlas becomes as important as its overall brightness. High-resolution images taken from both space and ground show that the object does not simply shed dust into a broad fan that trails away from the sun. Instead, there is a persistent, narrow feature that points in almost the opposite direction, a sunward extension that observers refer to as an anti-tail. The term is familiar in comet science, yet the specific form here is not. When the images are stacked and aligned, the anti-tail of 3I Atlas stretches across a length comparable to the distance from the Earth to its moon, yet remains only a small fraction of that length in width. It looks less like a plume spreading freely into space and more like a collimated stream of material that has somehow kept its coherence over hundreds of thousands of kilometers. To understand why this is peculiar, astronomers return to the basic forces acting on dust near a star. When a grain of dust leaves the surface of a cometary nucleus, it feels the pull of the sun's gravity and the much weaker gravity of the nucleus itself. But it also feels the push of sunlight and the effect of the solar wind. The ratio of the outward push to the inward pull depends strongly on the size of the grain. Very small grains, with a large surface area for their mass, can be accelerated significantly by radiation pressure. They are swept into extended tails that point roughly away from the sun, creating the familiar cometary shapes known from countless photographs. Larger grains, by contrast, feel gravity more strongly relative to the push of light. They move on paths closer to those of small, solid bodies, with only modest deflection from radiation. In most comets, the observed tails result from a mixture of grain sizes, and models that use reasonable distributions can reproduce the general shapes without difficulty. When these same models are applied to 3I Atlas, however, they encounter a problem. A simple cloud of mixed grains cannot easily produce a narrow, sunward-directed structure of the observed length that remains so straight over time. The geometry of the antitail, combined with its persistence over months, implies that the dominant grains in that feature are large, at least an order of magnitude or two larger than the fine dust often invoked. Calculations suggest sizes of around 10 to 100 micrometers, large enough that each grain behaves more like a tiny pebble than a wisp of smoke in the sunlight. The findings from the opposition surge reinforce this conclusion. A strong enhancement of backscattered light at very small phase angles tends to favor larger grains. And when the measured brightness profile is compared to scattering models, the result again points to a population skewed towards substantial particle sizes. From this, researchers infer that 3I Atlas is shedding unusually massive grains into space, and that many of these grains are being organized into the remarkable antitail. Yet even when the grain sizes are adjusted in the models, the full behavior of the dust refuses to fall neatly into place. The antitail not only extends sunward, but appears aligned with the direction of a jet that emerges from the nucleus and points toward the sun. This jet is present in images from the Hubble Space Telescope taken between late November and late December. a sequence of many exposures that reveals a consistent structure. Alongside the prominent sunward jet, there is a fainter jet pointing roughly away from the sun, as if the nucleus is launching material in two opposed directions. The sunward jet appears to feed the antitail, while the fainter jet feeds a less conspicuous, more conventional tail. Overlaid on this picture is a slow wobble, as the direction of the jets traces a cone in the sky. That wobble corresponds to the rotation of the object and gives a period of roughly several hours. The combination of large grains, dual jets, and rotational modulation creates a three-dimensional structure that is not easy to visualize from a single still image, and even harder to reproduce faithfully in one simple model. When dynamic specialists attempt to compute the paths of grains leaving the nucleus at various speeds and angles, subject to gravity and radiation pressure, they find regions of parameter space that come close to the observed antitail, but often at the expense of other constraints. To maintain a long, narrow, sunward-directed stream, grains must be ejected with velocities and timing that are finely tuned relative to the motion of the nucleus and the changing orientation of the jets. Small deviations tend to fan out the structure or break it apart over time. The fact that the actual antitail holds together so well across many weeks suggests either that the underlying conditions on the nucleus are remarkably stable, or that some guiding process is at work in the space around it. Both possibilities are intriguing. A very stable configuration would say something unusual about the internal structure of 3I Atlas, perhaps indicating strong, localized active regions that are anchored in specific topographic features and that respond to sunlight in a consistent way as the object rotates. A guiding process, by contrast, would hint at interactions with magnetic fields or plasma flows that are not yet fully captured in the current understanding of comet environments, or, in a more speculative direction, at external influences that impose order on the dust paths. At this stage, most discussion remains focused on natural causes. The antitail is examined in the context of previous comets that have shown similar but less extreme features. Projection effects can make physically broad structures appear narrow when viewed from certain angles, and the line of sight from Earth during particular parts of the orbit can emphasize a sunward extension that is not so striking in 3 dimensions. Analysts go back through archives of comet images, looking for precedents that might help demystify 3I Atlas. They find examples of narrow tails and structures aligned with the sun, but the combination of interstellar origin, large grain sizes, extreme polarization properties, and a long, sunward-directed antitail remains rare. The statistics of such features are uncertain because only a limited number of comets have been observed with comparable detail. Yet, the impression of an outlier remains. This is where the language of coincidence begins to appear more often in formal and informal discussions. Each trait by itself can be explained with some stretching of known parameters. A comet from interstellar space can, in principle, enter the solar system near the planetary plane. Grain sizes can, in principle, be biased toward larger values by the conditions on the nucleus. Jets can, in principle, be oriented in unusual directions and can produce temporary sunward structures if the viewing geometry is right. However, the probability that all these traits would be present together in one object is not obviously high. Researchers do not have a precise number for this probability, but they sense that the product of several low likelihoods can become very small. Some respond by noting that the solar system is large and observational campaigns are ongoing, so rare events are bound to appear eventually. Others, more open to broader possibilities, note that when an event looks like an outlier in several dimensions at once, it may be a sign that a new category of objects or processes is being glimpsed. In this context, the behavior of the dust around 3I Atlas takes on significance beyond the physics of grains alone. If large, coherent streams of particles can be maintained over hundreds of thousands of kilometers, they might act as tracers of forces or structures that are otherwise invisible. For example, if there were any interaction between the object and previously undetected fields, flows, or even artificial constructs in the outer solar system, the dust might reveal it by the way it bends, thickens, or thins along its length. No such obvious anomalies are seen in the images that exist, but the mere possibility that dust could act as a visible probe of hidden influences adds another layer of motivation to the study. For now, all that is clear is the stubbornness with which the antitail resists easy categorization. It is the visible record of a process that involves the internal properties of the nucleus, the ejection of large grains, the rotation of the object, and its interaction with solar radiation. Each of these components is understood in broad terms, but their combination here produces a structure that lies at the edge of current experience. As 3i Atlas moves onward along its open path, the antitail gradually changes and eventually fades. But the detailed measurements taken during its prime become part of a long-term archive. They will later be revisited in the light of new ideas, including those that reach beyond standard comet physics. The dust that seems at first to behave only a little differently from expectations thus becomes one of the central pieces of evidence in a case that will later draw attention from outside the usual astronomical community. For the moment, it is filed as an anomaly in grain dynamics. A note that the interstellar visitor carries with it material that does not entirely follow the script written by previous comets. As images of the antitail accumulate, another kind of measurement begins to define the mystery of 3i Atlas. This concerns polarization, the way the electric field of light oscillates as the wave travels. Sunlight leaving the sun is mostly unpolarized, with oscillations in many directions mixed together. When that light scatters from dust grains around a comet, the field can become partially aligned, producing polarized light whose degree and orientation depend on grain size, shape, composition, and on the phase angle, the angle between the sun, the object, and the observer. Over decades, astronomers have built a reference pattern for comets. At very small phase angles, polarization is usually slightly negative, then it turns positive and rises to a peak at intermediate angles before decreasing again. Different comets trace slightly different curves, but most follow this general shape closely enough that the behavior is treated as a standard. Against this backdrop, the first polarimetric measurements of 3i Atlas do not look routine. Even when the phase angle is not especially small, the light from the object shows strong negative polarization over a wider range of angles than usual. Negative polarization means that the preferred direction of the electric field oscillations is effectively rotated relative to the common expectation for scattered sunlight in that geometry. The effect is small to the unaided eye, but clear in precise data. When these measurements are compared with the accumulated archive for other comets, 3i Atlas sits at one end of the distribution, with more negative values than almost any previously recorded case. Some analyses describe the signature as extreme, perhaps unprecedented within the known comet sample. This raises an obvious expectation as the rare, near-perfect opposition in January approaches. If 3i Atlas were to behave like a slightly unusual member of the usual family, then adding measurements at very small phase angles should smooth out the curve, bringing it back toward the standard shape. Observing plans around opposition therefore gives special weight to polarimetry. Large telescopes and smaller, carefully calibrated instruments are pointed at the comet as the phase angle shrinks to less than a degree. When the resulting data are reduced and plotted, the curve that emerges does not relax into line. The negative polarization remains strong and persistent, and the overall pattern refuses to match the known empirical groups. In plain terms, the way 3i Atlas polarizes light does not fit easily into any existing category. Attention turns to the dust. The basic physics of polarization by small particles is well understood in principle, but intricate in detail. Theoretical treatments allow for many kinds of grains: compact fragments, irregular pieces, fluffy aggregates made of smaller units, layered grains with cores and mantles, and mixtures of ice and darker material. Each type has a characteristic polarization curve. Researchers now try to tune these models to match the new data, guided by independent hints from the opposition surge and from the antitail that the dominant grains are relatively large, roughly tens of micrometers across. Large grains often reduce the overall level of polarization, yet here the signal is both strong and strongly negative at small angles. To accommodate this, models introduce grains that are not only large, but also highly porous or internally structured, perhaps made of many subunits bound in an open network. Some such combinations can push the theoretical curves in the direction of the observations, but no single, simple configuration reproduces the whole pattern. When a model matches the extreme negative values at small phase angles, it tends to deviate at intermediate angles or at different wavelengths. The dust around 3i Atlas begins to look like it belongs to a regime not well sampled before. One natural explanation links this to the object's interstellar origin. A body that formed around another star and then spent long periods in deep space would experience a different history of irradiation, collisions, and thermal cycles than comets that remained bound to the sun. Over long times, cosmic rays and ultraviolet light can modify the outer layers of grains, changing their optical properties and internal structure. If 3i Atlas preserves such a surface record, then its unusual polarization curve may be a direct signature of that history, now revealed because the object happens to pass through a range of phase angles that allow detailed polarimetry. In this view, the anomaly is real, but natural, a sign that interstellar comets can carry dust with properties not common among local comets. At the same time, a more speculative thought appears at the edge of the discussion. Polarization is a way of encoding structure in light. On Earth, technologies deliberately shape polarization to control glare, transmit information, and separate signals. No serious analysis claims that the polarization of 3i Atlas carries an artificial message, yet the idea offers a useful test. If one imagines, purely as a thought experiment, a remote probe or passive device designed to be recognizable under certain viewing geometries, one might ask whether an unusual, robust polarization pattern at very small phase angles would be a plausible marker. The case of 3i Atlas then becomes a concrete example against which such ideas can be measured. The exercise does not prove any technological origin, but it sharpens the question of how contrived or how natural the required dust properties must be. Under strictly natural assumptions, the extreme negative polarization implies grains that are large, complex, and likely shaped by long interstellar processing, placing 3i Atlas at the edge of current experience. If future interstellar objects show similar behavior, the pattern may grow into evidence for a distinct population. If no such cases appear, this object will remain a lone outlier whose light refused to follow the usual rules. In either case, the polarization measurements taken around opposition become a central part of its record. Long after the comet itself has faded from the reach of telescopes, its polarization curve remains in archives, a compact summary of how sunlight, dust, and geometry interacted around this particular visitor. Embedded in that curve are clues about grain physics in formation environments, and, in the more speculative layers of interpretation, about how an interstellar traveler of any origin might appear when its presence is read not just in brightness and shape, but in the subtle orientation of the light it returns. While the polarization data are being analyzed, another pattern emerges from the images taken repeatedly over many weeks. The Hubble Space Telescope collects a sequence of exposures between the end of November and late December, and ground-based telescopes contribute their own time series. When these images are aligned and examined one after another, the jets of 3i Atlas do not stay fixed in the sky. The prominent jet that points roughly toward the sun and the fainter jet that points more nearly away both shift slowly in orientation, sweeping around an axis over a regular interval. The effect is reminiscent of a rotating beam passing over a distant landscape. In this case, the beams are streams of gas and dust being released from the surface of the object and traced by the sunlight they scatter. By tracking the position angle of the jets in each image and fitting a repeating pattern, astronomers infer that the nucleus of 3i Atlas is spinning with a period of several hours. Independently, they monitor the total brightness of the object over time. The light curve, when plotted, shows small but consistent rises and falls that repeat with the same period as the jet wobble. When the jets are oriented in ways that expose more illuminated material toward the observer, the object brightens. When the jets swing away, the brightness drops slightly. The agreement between the photometric period and the jet wobble period reinforces the conclusion that the nucleus has a well-defined rotation and that the jets are anchored to specific regions on its surface that come in and out of view as it spins. This picture of a rotating body with localized active sources is familiar in comet science. Yet in 3i Atlas, the details are again unusual. The main jet is oriented roughly toward the sun, feeding the long antitail that stretches sunward. A secondary jet extends in the opposite direction, contributing to a more conventional tail. As the object rotates, both jets trace out cones in space. But because the motion is projected onto the two-dimensional sky, the paths appear as gentle swings of the features around the nucleus. From the amplitude and phase of these swings, and from the known orbital geometry, researchers reconstruct the approximate orientation of the spin axis relative to the direction of the sun and to the plane of the planets. The result is another geometric coincidence. At large distances from the sun, the spin axis of 3i Atlas appears to align within roughly 10 to 20 degrees of the direction toward the star. This means that as the object journeys inward, one of its poles, the region from which the main jet likely emerges, tends to face the sun more directly than would be expected for a random orientation. For a natural body drawn from a cloud of many possible directions, there is no simple reason why its spin axis should favor the solar direction in this way. The alignment could be coincidence, a chance outcome of the distribution of interstellar comets and the selection biases of detection. It could also be the result of subtle torques from outgassing over long times, gradually steering the spin axis into a preferred orientation. However, the time available for such evolution is limited by the object's active lifetime, and modeling the cumulative effects of gas jets on rotation over many passages is difficult, especially for an object that has not, as far as is known, repeatedly visited the inner solar system. Whatever the explanation, the alignment adds one more entry to the growing list of low-probability features. The path of the object lies close to the planetary plane. The date of its near-perfect opposition with Earth and Sun falls at a time when it is both active and observable. The spin axis points roughly along the solar direction at large distances. Its jets, anchored near the poles, therefore tend to sweep material into structures that are also favorably placed for observation. The long sunward antitail is one direct result of this configuration. Seen together, the path, the timing, and the rotation create a picture in which 3I Atlas appears to cooperate with observational convenience more than strict randomness would suggest. In discussions that remain anchored in conservative interpretations, researchers note that rare alignments do happen and that the observational focus on unusual objects may itself amplify the sense of improbability. Yet, the data themselves continue to invite deeper questions. If the spin axis alignment is not purely chance, what mechanism could have established it? One possibility considered within the natural framework is that when 3I Atlas was still far from the Sun, small asymmetries in outgassing slowly nudged its rotation over time. Even in interstellar space, weak but persistent torques from thermal forces or from anisotropic radiation could play a role. Another possibility is that the object was already spinning in this orientation when it left its system of origin, perhaps as a result of processes during its formation or ejection. In that case, 3I Atlas would carry a memory of conditions around another star, encoded in the direction of its spin. The observed alignment would then be a coincidence relative to our Sun, but not necessarily random with respect to its original environment. Parallel to these natural explanations, a more speculative line of thought emerges. If one imagines a device or vehicle designed to sample the solar environment, a stable rotation that keeps a preferred region facing the Sun for extended periods could be advantageous. Instruments, power systems, or communication components placed near a pole that remains sunward would experience steady illumination. Jets or other emission features aligned with that pole might act as markers visible from afar, especially when combined with gravitational assists near planets. The regular wobble of the jets could, in principle, serve as a timing reference or scanning pattern. In this view, the behavior of 3I Atlas would resemble that of a rotating platform that surveys its surroundings as it moves through the solar system, its jets tracing out surfaces in space in a controlled manner. No observational evidence demands this interpretation, and the data can still be read as arising from a complex but natural comet. Nevertheless, the detailed character of the jet wobble and the alignment of the spin axis offer an empirical basis for such speculation. They define what an interstellar traveler with simple, observable markers might look like, should such an entity exist. The key is that all of the required traits have now been documented in one real object. Independently of any technological hypothesis, the rotation of 3I Atlas remains scientifically important. Knowing the spin period and axis orientation allows more accurate modeling of its thermal evolution, its outgassing patterns, and the stresses on its interior. These, in turn, affect the rate at which material is lost, the stability of its surface layers, and the way cracks and jets develop. If the spin period were to change measurably over time, that change would provide direct information about the strength and direction of torques from the escaping gas. Some early data suggest that the period after closest approach to the Sun is stable within the uncertainties, but the time baseline is still short. Continued monitoring could reveal subtle shifts that would either support or challenge models of jet-driven rotational evolution. For now, the picture is of a nucleus that rotates steadily, with jets emerging from near its poles, wobbling in a regular pattern that matches the brightness variations and that feeds a distinctive dust architecture. The regularity of the wobble contrasts with the irregularity of the object's origin and orbit, and this contrast itself feeds the overall sense of mystery. The rotation turns 3I Atlas from a simple point of light into a structured, dynamic system, one whose internal clockwork can be traced from the pattern of light and dust alone. As it continues along its hyperbolic path, carrying its spin and jets with it into deeper space, the record of that motion remains fixed in observations taken over a small slice of its immense journey. Later, when the object is far beyond the reach of telescopes, the sequence of wobbling jets will still offer a compact description of how this particular interstellar visitor turned and breathed as it passed briefly through the inner solar system. From the moment 3I Atlas is recognized as an interstellar object, its path is traced not only backward into the distant cloud that surrounds the solar system, but also forward into the years that follow its departure from the inner regions. Dynamical models show that long before it flared into view, the object traveled inward from the outskirts, taking on the order of 8,000 years to drift from the remote reservoir of icy bodies toward the realm of the planets. For most of that time, it remained dark, a cold fragment carrying whatever record its surface holds of another star and of the interstellar space between systems. Only when it approached the sun closely enough for ice to sublimate did it become visible, surrounded by gas and dust, and marked by the distinctive jets and antitail that now define its case. After perihelion, as it rounds the sun and begins to move outward, its orbit remains hyperbolic. It is not bound to the star and will eventually leave the solar system altogether. Yet, its path will bring it near one of the major gravitational centers in the planetary system before it goes. Calculations show that on a date in mid-March of a coming year, 3I Atlas will pass close to Jupiter, at a distance comparable to the boundary where the giant planet's gravity dominates over the pull of the sun for small nearby bodies. This boundary, often called the Hill radius, marks the region within which moons can orbit a planet stably. For a natural interstellar visitor, the chance of passing near this specific zone is not impossible, but it is low enough to be noted. The same models that reconstruct the long inward journey now project a brief, crucial passage near Jupiter, a kind of encounter with a gateway where material can, in principle, be captured or redirected. In the natural picture, the object simply continues on its way, its trajectory bent slightly by the combined pull of the planet and the star, but not enough to trap it. It swings past, sheds more material, and then escapes into interstellar space, leaving behind only a faint memory in the form of dust and small fragments. However, when the geometry is examined closely, another possibility emerges. If 3I Atlas were to release pieces of itself at just the right moment near this boundary, those pieces could lose enough of their motion relative to Jupiter to become gravitationally bound as new irregular moons. For this to happen, the fragments would need to be given a slight slowdown relative to the main body, canceling part of their outward speed away from the sun, so that Jupiter's gravity could take over. In simple mechanical terms, they would have to shed the hyperbolic excess speed that carries the parent body out of the system. The range of velocities and directions that accomplish this is narrow. A fragment ejected too fast would escape with the parent. A fragment ejected in the wrong direction would either fall into the planet, skim past it, or continue on an independent escape path. Only a small subset of possible ejection conditions would place a daughter object into a stable orbit around Jupiter. In natural scenarios, fragmentation does occur. Comets can break apart under thermal stress, tidal forces, or internal weakness when they pass near massive bodies. Yet, those breakups usually produce families of pieces that share similar orbits, still unbound or captured in broad ways that do not require precise tuning. The thought that an interstellar comet might shed fragments in such a way that a few of them come to rest exactly within the planet's gravitational domain at the edge of its Hill sphere is therefore intriguing. It is possible, but in the language of probabilities, it belongs to the tail of the distribution. This is where speculation begins to layer itself over the solid framework of orbital mechanics. If one were to imagine a device, or carrier, designed to traverse the solar system and leave behind long-lived assets in strategic locations, a close pass by Jupiter at the boundary of its gravitational influence would be an attractive opportunity. The planet's moons offer stable platforms from which to observe or relay information, and the region within its Hill radius can hold small artificial satellites for long periods. An interstellar craft that released small units during such a passage could, in principle, seed the Jovian system with watchers or data stores without requiring large propulsion systems on each unit. The main body would simply act as a delivery vehicle, using the gravity of the planet and the sun to perform most of the work. In this speculative frame, the path of 3I Atlas starts to look like a planned route. It arrives from interstellar space along a trajectory aligned with the planetary plane, activates near the sun, reveals distinct jets and a long sunward anti-tail, and then heads outward on a course that intersects the edge of Jupiter's gravitational domain. At each stage, the geometry appears unusually convenient for observation and for potential interaction with major bodies. None of this proves design. Orbital distributions are broad, And in a large enough sample, some paths will pass near giant planets at special radii simply by chance. The current observational record of interstellar comets is too small to define what is typical. Still, the specific combination of interstellar origin, planetary plane alignment, rare opposition with Earth and Sun, and forthcoming encounter near the Hill boundary stands out. This is why the projected March approach to Jupiter becomes an important checkpoint. Spacecraft are already present in the Jovian system, including missions from NASA such as Juno that orbit the planet, and missions from the European Space Agency and from NASA are on their way toward its moons. Together, these platforms provide multiple eyes on the region through which 3I Atlas will pass. If nothing unusual happens, the object will swing by, its presence recorded only as a small perturbation in the gravitational environment and as a transient point of light in telescope logs. That outcome would still be informative, confirming that even in this carefully calculated geometry, the visitor behaves like a natural body, leaving no lasting trace beyond its dust. If, on the other hand, new small objects were to appear on orbits around Jupiter that cannot be easily traced to known sources, or if subtle anomalies in the local environment were detected following the passage, the case file of 3I Atlas would change substantially. The difficulty is that the Jovian system is already rich and complex, with many small moons and ongoing influxes of material. Distinguishing a new fragment that arrived with an interstellar comet from the background of other debris would require detailed tracking and modeling. The window for direct association might be narrow. Nonetheless, the possibility that the approach could leave observable signatures is enough to turn attention toward that date in the future. In practical terms, it encourages careful archiving of current observations of the Jovian environment, so that any later changes can be compared against a baseline. In conceptual terms, it deepens the sense that 3I Atlas is weaving through key locations in the solar system in a way that may or may not be purely random. Its long journey from the distant cloud, its brief flare near the Sun, and its projected meeting with Jupiter's gravitational boundary together outline a path that invites both cautious analysis and wider speculation. The same equations of motion that describe every comet and asteroid now also describe this interstellar visitor, but the particular initial conditions it carries and the particular alignments it passes through make it an especially sensitive test of how much of reality is captured by the phrase random encounter, and how much might one day require a broader category. As the scientific work on 3I Atlas becomes more detailed, information about the object spreads gradually beyond the technical literature and specialist meetings. Reports filter into public awareness that this interstellar visitor shows a long sunward antitail, extreme negative polarization, a spin axis aligned in a curious way with the Sun, and a future path that passes close to the boundary of Jupiter's gravitational influence. Together with the fact that it originates from beyond the solar system, these features are enough to draw the interest not only of astronomers, but also of people who think in terms of low-probability, high-impact events. In the modern world, that category includes intelligence agencies. Within the scientific community, the interest of such agencies is not entirely surprising. The distinction between purely natural and potentially technological phenomena has practical consequences. An object that might, even in speculative terms, represent a technological artifact from an unknown civilization has implications for risk, for opportunity, and for the management of public reaction. At the same time, unusual celestial events can be misread or misrepresented, either intentionally or accidentally, in ways that affect stability on Earth. An interstellar body that behaves in a way some interpret as possibly artificial could become a focus of narratives that agencies are required to understand and, if necessary, to anticipate. Against this backdrop, requests for documents begin to be filed under national transparency laws. Researchers, journalists, and interested citizens submit formal applications for any records held by major agencies concerning 3I Atlas. Among those agencies is the Central Intelligence Agency, which has long established procedures for handling such requests. For many subjects, the response is straightforward. If no records exist, the reply states that fact. If records do exist and can be released, they are provided with appropriate redactions. In some cases, however, a different formula appears, signaling that even the presence or absence of material is treated as sensitive. In the case of 3I Atlas, the reply that emerges does not simply state that no information is held. Instead, it uses the familiar phrasing that the agency can neither confirm nor deny the existence of records on this subject. This type of answer has been used historically in areas where acknowledging the existence of records would itself reveal classified activity, investigative interest, or operational involvement. It is a way of closing off inference from the pattern of responses alone. When applied to an interstellar comet, it therefore acquires special significance in the eyes of observers who follow both the scientific and security aspects of the story. In principle, such a reply does not prove that records exist. It asserts only that whether they do or not is itself information that cannot be made public. Nevertheless, the departure from the simpler statement of no records suggests that the question has been considered internally. There has been enough discussion or involvement that a routine denial would be misleading, or would conflict with broader classification rules. The exact nature of that involvement remains unknown and may range from brief analytical notes to more detailed assessments. In open commentary, scientists who are accustomed to dealing with data rather than classified responses treat this development cautiously. Some note that in a world where intelligence agencies are expected to monitor any phenomenon that could be misinterpreted or exploited, it is natural that a strange interstellar object would at least cross someone's desk. Others point out that the same response has been used in contexts that later turned out to involve active programs, suggesting that 3I Atlas has been examined within frameworks designed to evaluate unconventional threats or opportunities. The truth may lie somewhere between these poles. From the perspective of an agency tasked with anticipating hazards, several features of the object are noteworthy. Its status as an interstellar visitor means it comes from an unknown environment. Its path through the planetary plane and its close approach to Jupiter places it in regions of high strategic interest. Its electromagnetic behavior, including its unusual polarization and its capacity to reflect or scatter light in unexpected ways, might interact with sensor systems designed for early warning, leading to false positives or ambiguous signals. Evaluating whether such interactions are possible is a rational task for specialists in technical intelligence. Internally, analysts might also consider very low probability scenarios in which the object is not merely a natural body. If, for example, a non-terrestrial civilization were capable of sending probes into other systems, an interstellar comet would be one of the few kinds of object that could plausibly mask such activity. A carrier disguised as a natural fragment could pass through outer sensor networks with little notice. Even if the likelihood of the scenario is judged extremely low, the potential impact of being wrong could be high. Modern risk frameworks are built to pay attention to such combinations. From this angle, a review of the available scientific data on 3I Atlas, supplemented by any relevant sensor observations, would be a responsible precaution. None of these considerations require an extraordinary explanation. They follow from standard practices in managing uncertainty about novel events. However, once the official response declines to confirm or deny the existence of records, the interpretation of outside observers naturally widens. Some see the answer as an admission that 3I Atlas has been treated as a possible black swan event, a rare occurrence with disproportionate consequences. The anomalies in its behavior, from the long antitail to the projected pass near Jupiter's hill boundary, are then seen as triggers for internal review. In this view, the agency's main concern would be to ensure that the object poses no immediate threat to Earth, does not interfere with critical space infrastructure, and does not signal an adversary's attempt to test or spoof detection systems. Once these boxes are checked and the risk is assessed as acceptable, the matter can be filed away. At the same time, the refusal to provide more detail can be interpreted as an effort to avoid feeding speculation in the public arena. Any acknowledgement that an intelligence agency has classified interest in an interstellar object could be used to support narratives that go far beyond the data, including claims about contact, cover-ups, or hidden programs. By declining to confirm or deny record holdings, the agency maintains a neutral surface while preserving internal freedom to study the issue as it sees fit. The scientific narrative and the intelligence narrative thus diverge. In the open, 3I Atlas is described in terms of polarization curves, dust grain sizes, jet wobble, and orbital dynamics. In the classified realm, if any such realm indeed exists for this object, it would be described in terms of risk matrices, sensor signatures, and scenario planning. The same underlying facts would be examined through different lenses. The public only sees the scientific side and a single, carefully worded sentence from the other side. That sentence is enough, however, to add a new layer of mystery to an object that already challenges easy categorization. The presence of an intelligence agency in this story changes the way future data are anticipated. If new anomalies appear as 3I Atlas approaches Jupiter, or if unexpected signatures are detected in its vicinity, observers will naturally wonder whether those results are being examined not only by astronomers, but also by analysts whose work remains unseen. The knowledge that a line has been drawn around certain kinds of information sharpens the contrast between what is known and what is withheld, even if the motive for withholding is mundane. In this way, the simple phrase that neither confirms nor denies the existence of records becomes another data point in the broader case. It illustrates that the strangeness of Three-Eye Atlas is not just an abstract problem in celestial mechanics, but also a matter of institutional attention. An interstellar object has moved from the sky into the frameworks of organizations built to think about uncertainty, secrecy, and security. Whether that attention ultimately matters for understanding the object's true nature is an open question. For now, it confirms at least that Three-Eye Atlas sits at the intersection of scientific curiosity and strategic caution, a place where even the absence of clear answers can itself become part of the mystery. As data and institutional reactions accumulate, the question of what Three-Eye Atlas actually is begins to take a more structured shape. On one side lies the interpretation of a natural relic, a fragment of another planetary system that happens to pass through the solar system and, by chance, displays several unusual combinations of properties. On the other lies the more speculative possibility that it is, or contains, something engineered, a device or artifact whose path and behavior are not entirely accidental. The narrative does not need to choose between these possibilities to examine how each fits the known facts. It starts from the secure ground of observation. Three-Eye Atlas moves on a hyperbolic orbit, a clear sign that it is not gravitationally bound to the Sun. Its approach from the direction of the distant cloud, its journey inward over thousands of years, and its eventual escape after perihelion are all well described by standard celestial mechanics. As it nears the Sun, it behaves in many ways like a comet. Ice sublimates, gas jets arise, dust is carried away from the nucleus, and a coma forms. Spectra show familiar components, and the inferred sizes of the dust grains, though skewed toward larger values, still fall within a range that laboratory physics can handle. The opposition surge observed in January, along with the negative polarization pattern, can be modeled by invoking complex grains shaped by long exposure to radiation. The long antitail, while striking, can in principle emerge from a combination of large grains, jet geometry, and viewing angle. The alignment of its path with the planetary plane and of its spin axis with the solar direction may be drawn from the tail of plausible distributions. Its future pass near the boundary of Jupiter's gravitational domain may qualify as an unlikely but not impossible event. In the natural relic view, Three-Eye Atlas is an outlier, but outliers are expected in any sufficiently large sample, and the small number of interstellar objects discovered so far may bias perception. The fact that earlier interstellar visitors also showed unexpected traits supports the idea that the population as a whole occupies regions of parameter space that local comets rarely explore. Under this assumption, Three-Eye Atlas is the first detailed glimpse of interstellar comet dust physics under a fortunate set of geometries, not a deliberate messenger. Its anomalies become clues to processes in distant protoplanetary disks and to the long-term chemical and structural evolution of small bodies wandering between stars. The surface of its grains may record radiation histories unlike those endured by local comets. Its internal layering might preserve information about temperature gradients and collisions in an alien system. Even its spin axis and jet patterns could reflect formation scenarios around another star, later modified only slightly by interactions with interstellar space and with the Sun. In this frame, the task is to extract as much astrophysical information as possible from the limited window of observation, using every tool from polarimetry to dynamical modeling. The more speculative interpretation asks a different question. Given the observed behavior of Three-Eye Atlas, is it reasonable even to entertain the idea that it might be, or contain, a technological construct? The first step in addressing this is to note what has already been looked for and not found. Among the searches conducted during its passage is a campaign by groups involved in the search for extraterrestrial intelligence, using radio telescopes to listen for signals from the object. For several hours of observing time, sensitive receivers scan a range of frequencies, looking for narrowband or patterned emissions that stand above the natural radio noise. The result is negative within the limits of the experiment. No clear artificial signals are detected. On the surface, this might appear to weigh against the engineered traveler hypothesis. However, a closer look at the geometry and timescales involved suggests that the non-detection does not carry heavy weight. Three-Eye Atlas has spent roughly 8,000 years traveling inward from the outer regions toward the inner solar system, and its full journey through interstellar space before that likely extends over far longer periods. The radio search, by contrast, covers only a few hours, a tiny fraction of the total time the object has existed and moved. If one imagines an interstellar device designed by an unknown civilization, it is not obvious that it would transmit radio signals continuously, or in a way that aligns with the frequency range and beam pattern used in the search. It might communicate rarely, or at frequencies outside the observed band, or by methods entirely different from radio. It might be a passive probe designed only to silently record, or a one-way data courier that transmits a burst of information after leaving the solar system rather than during its passage. In human terms, it would be like attempting to judge whether a distant city is active by listening for a few hours at a single wavelength during a single evening. A null result under those conditions is informative only in a limited way. A related consideration concerns the timescale for communication across the galaxy. Light takes tens of thousands of years to cross the Milky Way from one end to another. For any civilization separated by such distances, real-time conversations using light-speed signals are impractical. A more plausible pattern of operation for an interstellar probe, whether natural in its origin or artificially guided, would be to act autonomously, making its own decisions based on onboard information and transmitting data only at carefully chosen moments, perhaps after completing a survey or leaving a region of interest. The idea that it would respond to a brief, unsolicited listening window from a young technological species in one of the many systems it passes is speculative at best. In this light, the absence of a detected signal from 3I Atlas tells more about the limits of current search strategies than about the true nature of the object. Within this speculative framework, the observed features of 3I Atlas take on new potential meanings. The alignment of its path with the planetary plane could be seen as an efficient way to encounter multiple worlds in a single pass. The near-perfect opposition with Earth and Sun might be a byproduct of a trajectory designed to maximize opportunities for illumination and observation from both the object and the planetary system it visits. The spin-axis alignment with the solar direction, coupled with a prominent sunward jet and anti-tail, could be interpreted as a form of passive signaling, a way to stand out against the background population of comets when viewed under the right conditions. The approach to the boundary of Jupiter's gravitational influence might represent an intentional use of a planetary gateway to deploy or adjust subsidiary units. None of these interpretations are required by the data, but the data do not preclude them. They show that an object with an apparently natural composition and cometary behavior can also follow a path and display geometries that would make sense for a probe designed with a modest understanding of celestial mechanics. The question then shifts from whether 3I Atlas is artificial to whether there is any unique observational feature that would distinguish a cleverly guided, natural-looking traveler from a genuine natural relic. At present, such a feature has not been identified. The polarization, dust structures, and dynamical properties can all be housed within elaborate natural models, even if those models are stretched and complex. No unambiguous sign of machinery, structural regularity, or persistent signal has been found. The involvement of intelligence agencies adds an institutional layer of interest, but does not by itself provide physical evidence. The prudent stance, therefore, remains agnostic. 3. I-Atlas is treated as a natural interstellar comet with unusual properties, while the door to more exotic interpretations stays formally open. This balanced view acknowledges the limitations of current knowledge without jumping to conclusions. It also guides future observing strategies for upcoming interstellar visitors. If another object appears with similar alignments, similar polarization extremes, and another carefully placed pass near a giant planet, the pattern would become more than a single case. A repeated set of traits across multiple objects would sharpen the argument that something systematic is at work, whether natural or artificial. Until then, 3I Atlas occupies a singular position as an interstellar traveler whose behavior can be read in two ways, one conservative and one speculative, both constrained by the same set of carefully gathered data. It remains an example of how a single object can sit at the boundary between categories, forcing observers to refine both their natural models and their imaginations about what, in principle, a visiting artifact might look like. In that sense, even without any definitive conclusion, it has already changed the way the solar neighborhood is watched. As the debate about the nature of 3I Atlas continues, attention turns not only outward to Jupiter and the distant interstellar path, but also inward to the nearby worlds that humans plan to explore more thoroughly in the coming decades. Among these, the Moon and Mars stand out as quiet archives of solar system history, surfaces that have preserved impacts and debris over billions of years in ways the Earth cannot. In this broader context, the interstellar visitor is no longer viewed only as a transient point of light, but as part of a chain of material that may already have left marks on these neighboring bodies. The Moon, lacking a thick atmosphere and significant geological activity, acts as a long-term collector. For roughly 4.5 billion years, small objects have struck its surface without being slowed or burned by air. The Earth, with its protective envelope, destroys or heavily alters most bodies smaller than about a few meters before they can reach the ground. The Moon does not. Fragments of comets, asteroids, and even interstellar objects can arrive largely intact, embedding themselves in regolith layers that build up slowly over time. In that sense, the lunar surface is a museum of impacts, storing pieces of material from many epochs and likely from many origins. If interstellar comets similar to 3I Atlas have been passing through the solar system over long periods, some fraction of their debris may already rest on the Moon, mixed with dust and rock chips from countless other sources. This possibility gives additional weight to planned missions that aim not just to visit, but to establish a sustained presence there. Programs such as NASA's Artemis series, which include a crewed flight around the Moon followed by future landings, are framed in official language in terms of exploration, scientific discovery, and strategic presence. In the context of 3I Atlas, they also become opportunities to sample the archive of the solar system and beyond. A well-designed survey of impact sites and regolith composition could, in principle, reveal exotic materials or structures that hint at origins outside the local system. The same instruments that search for ancient volcanic activity, water ice deposits, and traces of the early solar environment could be tuned to look for isotopic ratios, mineral assemblages, or microstructures that match those inferred from interstellar visitors. The Moon's advantages extend beyond its role as a collector. Its lack of atmosphere and its stable surface make it an ideal platform for astronomical observatories. Telescopes placed on the far side, shielded from Earth's radio noise, could conduct deep, quiet surveys of the sky in wavelengths that are difficult to observe from the ground. Optical and infrared instruments would benefit from the absence of atmospheric turbulence, and radio arrays could map faint emissions with unprecedented clarity. The idea of placing a gravitational wave detector on the Moon has also been discussed, leveraging the low seismic noise and stable ground to probe lower frequencies than are accessible on Earth. Such facilities would not only study distant black holes and cosmic events, but could also, incidentally, refine the census of small bodies passing through the solar neighborhood. A network of lunar and orbital observatories might detect interstellar objects earlier and track them more precisely, providing richer data on the kinds of anomalies seen in 3I Atlas. Mars offers a different but complementary record. For roughly half of its history, the planet is believed to have had a thicker atmosphere and liquid water on its surface. Later, it lost most of that atmosphere, leaving a thin envelope that offers only limited protection from incoming objects. Like the Moon, Mars preserves impacts, though modified by its own climate history. It is also a target in the search for past or present life, both microbial and more complex. In the context of interstellar visitors, Mars represents another kind of museum, one that stores not only physical fragments, but also possible chemical signatures of ancient interactions with external material. If objects like 3I Atlas have passed through the solar system long before humans existed, some may have intersected Mars, delivering exotic organics or complex molecules produced in other systems. Over time, these contributions would have been mixed into the Martian soil and rocks. Rovers and landers already exploring the planet sample only a tiny fraction of its surface. But as missions expand and human presence eventually becomes possible, more systematic surveys may be carried out. The concept of the Moon and Mars as museums connects back to the question of technological artifacts as well. If a technological civilization elsewhere in the galaxy has ever sent probes into the solar system, or if remnants of such probes have wandered here as debris, the most likely places for them to remain preserved would be airless or near-airless worlds with limited geological recycling. The Earth's active crust, weather, and biology erase most traces over long times. The Moon and Mars, by contrast, change slowly. Objects that land or crash there can remain for very long durations, buried gradually by dust, but still accessible to careful surveys. In this light, human plans to build bases and observatories on these worlds take on an additional layer of significance. A settlement on the Moon, equipped with rovers, drilling systems, and analytical laboratories, could conduct targeted searches for non-natural materials among the regolith. These searches could be framed in broad scientific terms, looking for any anomalies in composition or structure, not only those tied to 3I Atlas. Similar activities on Mars, especially in regions where impact ejecta are exposed, could extend the search. None of this requires an assumption that such artifacts exist. It simply recognizes that, if they do, the Moon and Mars are the most plausible locations to find them. The story of 3I Atlas helps to sharpen this reasoning. Here is an interstellar object that clearly arrives from outside, carries unusual dust and polarization signatures, and follows a path through key regions of the solar system. It demonstrates that interstellar material can and does traverse the space near the Earth and the Moon. It suggests that over geological timescales, many such objects, both ordinary and anomalous, may have done the same. Some fraction of their mass would have intersected the lunar and Martian surfaces. The interstellar comet thus becomes a contemporary example of a process that has been operating quietly for billions of years. At the same time, the planned human missions underline the fact that the solar system is moving into a new phase, in which its own inhabitants can actively investigate this accumulated record. The same rockets that carry crews to lunar orbit or Mars transfer orbits also carry instruments whose sensitivity and resolution far exceed those of earlier generations. Human presence allows flexible decision-making on-site, enabling investigators to respond to unexpected findings in real time. A strange shard embedded in regolith, an unusual isotopic pattern in a core sample, or a peculiar geometry in a buried structure could be examined immediately, rather than waiting for a future mission. Even if no non-natural artifacts are ever found, the systematic exploration of these museums will enrich understanding of the solar system's bombardment history and of the contribution of interstellar bodies to planetary surfaces. More importantly, it will change the context in which objects like 3I Atlas are interpreted. Future interstellar visitors will not be studied only from afar, with light curves and spectra, but against a growing background of direct measurements of material that has already fallen onto nearby worlds. The gap between observing an interstellar body in space and sampling its kin on the ground will gradually narrow. In the narrative of 3I Atlas, the Moon and Mars therefore act as quiet, waiting stages. They hold records that may connect to the strange dust, the peculiar polarization, and the geometric coincidences associated with the current visitor. Human missions to these worlds, driven by their own agendas of science, exploration, and strategy, also become part of a larger effort to understand how often material like this passes through, what marks it leaves, and whether the solar system has ever hosted not just natural debris from other stars, but deliberate artifacts. In this way, the interstellar comet and the dusty surfaces of two nearby worlds are linked in a single extended investigation that spans time, distance, and many kinds of evidence, from the faintest polarized light in deep space to the microscopic grains sifted through in laboratories on alien soil. As the passage of 3I Atlas recedes in time, the record it leaves behind settles into multiple layers. There are the raw data streams from telescopes, filled with brightness values, polarization angles, and position measurements. There are the processed products, plots of light curves and phase functions, images annotated with jet directions and anti-tail lengths, orbital diagrams showing the hyperbolic path threading through the planetary plane and past the boundary of Jupiter's gravitational reach. There are the scientific papers that interpret these, framing the object as an interstellar comet whose dust and geometry place it at the edge of existing understanding. There are also internal assessments within institutions that think about risk and secrecy, treating the same object as a low-probability event with potentially large implications. Above all, there is a quieter layer, the way the case of 3I Atlas reshapes a sense of what might be passing through the solar system unnoticed. In current cosmology, most of the mass and energy in the universe is assigned to components that do not interact with light in familiar ways, commonly labeled dark matter and dark energy. These terms stand not for detailed understanding, but for placeholders, acknowledgments that visible matter and radiation represent only a small fraction of what exists. In a similar way, the inventory of known comets, asteroids, and interstellar visitors may represent only a thin slice of the bodies that actually move through the outer regions of the solar system and beyond. Detection biases favor objects that are relatively bright, that cross close to the Sun, or that pass near the Earth. An object like 3I Atlas is seen precisely because it satisfies several of these conditions, and because survey systems happen to cover the relevant parts of the sky. Many other bodies may follow less convenient paths, remaining unobserved or only briefly recorded as faint streaks with insufficient data for classification. The notion of unknown unknowns, of entities or processes that lie entirely outside current frameworks, is therefore not an abstract philosophical idea, but a practical consideration. Human instruments and models are designed and tuned based on what has already been noticed. Telescopes search particular wavelengths, software filters highlight familiar patterns, and theories grow around the accumulated sample. An object that deviates too far from those expectations may still be recorded, but classified as an outlier to be set aside or folded back into existing categories with additional complexity. In the sample of 1 provided by 3i Atlas, the combination of extreme negative polarization, long sunward anti-tail, unusual geometric alignments, and a projected pass near a planetary gravitational boundary pushes at those categories but does not break them. It remains possible to accommodate all features within a natural picture, given enough parameters and carefully tuned models. At the same time, the object demonstrates that reality can arrange these features in ways that had not been anticipated. It suggests that there may be other configurations, as yet unseen, that would stretch the models further, perhaps to the point where the natural explanation becomes strained beyond usefulness. Human imagination is limited by experience. The technology is now in use, from radio telescopes and space observatories to machine learning systems that classify sky surveys, are trained on earlier data. They excel at recognizing patterns that resemble known objects and behaviors. They are less reliable when faced with phenomena that have no close analogs in the training set. A device from another civilization, designed according to principles and constraints that differ from human engineering, might interact with the environment in ways that do not resemble familiar satellites, probes, or debris. Its emissions, if any, might not be confined to the narrow radio bands that current searches examine. Its structure might mimic natural geometry by design, or it might exploit physical effects that are not yet widely understood. In such a scenario, the first contact with such an artifact would likely occur not as a clear signal, but as an anomaly in data that analysts are tempted to attribute to noise, calibration error, or an unusual but natural object. 3i Atlas sits precisely at this boundary. It is undeniably real, it shows measurable deviations from the norm, and it has attracted attention from both scientists and agencies. Yet, it can still be classed as a comet, given enough flexibility in the description of its dust and dynamics. The decision to stop there, to treat it as a natural relic and leave more exotic interpretations formally unproven, is appropriate given the evidence. It is also a reminder that future cases may prompt the same cycle of initial surprise, model adjustment, and eventual assimilation into the natural category, unless something unambiguously artificial is discovered. In this sense, the case file of 3i Atlas remains open, not because evidence is withheld, but because the framework for recognizing truly non-natural phenomena is still under construction. The planned encounter with the boundary of Jupiter's gravitational domain, the negative result of brief radio searches, the refusal of an intelligence agency to confirm or deny the existence of records, and the ongoing expansion of human presence to the Moon and Mars all form parts of a larger picture in which the solar system is becoming both more monitored and more accessible. Each new interstellar visitor will enter a domain that is better instrumented than the last. Spacecraft in orbit around planets, observatories on the lunar surface, networks of ground-based telescopes coordinated in real time, and increasingly sensitive detectors of gravitational waves and high-energy particles will together provide a denser mesh through which anomalies must pass. At the same time, the volume of data will grow to the point where human analysts cannot inspect every unusual pattern directly. Automated systems will filter and classify, and their designs will carry implicit assumptions about what is interesting and what can be dismissed. In this evolving environment, the lesson of 3i Atlas is not that a hidden artifact has been missed, but that the space of possible signals and structures is wider than previously appreciated. A single object has shown that interstellar comets can trace paths that skim planetary planes, produce dust structures that defy simple expectations, and present polarization signatures that sit at the edge of known distributions. It has encountered a world in which both astronomers and intelligence agencies take notice, in which a freedom of information request about a cosmic body can result in a reply crafted for matters of terrestrial secrecy, and in which human plans extend toward the airless surfaces that quietly hold the long-term record of similar passages. The mystery that remains is not tied to one object alone. It concerns the larger question of how many such visitors have come and gone without comparable scrutiny, and how many more will cross the inner system in centuries to come. Some will be ordinary by any standard. Others may resemble 3i Atlas, combining rare alignments and physical anomalies in ways that challenge current understanding but still admit natural interpretations. A few, perhaps, could fall outside even these broadened categories, forcing a reconsideration of what counts as evidence for something more than ice and rock shaped by stars. For now, the dossier on 3I Atlas closes with unresolved entries. The origin of its extreme negative polarization, the full three-dimensional structure of its antitail, the reasons for its specific geometric coincidences, and the eventual outcome of its passage near Jupiter's gravitational boundary remain topics for ongoing study and future observation. Its journey from the distant cloud to the inner solar system and back outward again has been tracked for only a tiny fraction of its full trajectory through space and time. The rest lies beyond current view. Human observers return to their instruments, models, and plans, aware that somewhere beyond the reach of their telescopes, this interstellar traveler continues silently along its hyperbolic path, carrying with it dust grains whose properties record histories not yet fully read. The sky above holds many such paths, most unseen, some destined to intersect the solar system in ways that will again prompt careful measurements, cautious interpretations, and renewed speculation about what kinds of objects, natural or otherwise, move between the stars. In that ongoing process, the memory of 3I Atlas serves as both a data point and a question mark, a reminder that even with detailed observations, some cases resist firm closure, and instead leave behind a sustained, open wonder about what else might be out there, passing briefly through the shared space between suns before disappearing once more into the dark.